So we were on this slide, Kerberos Exchange. Just to remind you again, Kerberos is a system for user authentication protocol developed at MIT. And that way you could log in at any place in the campus and use any services anywhere on the campus. All right? And they did this by using a KDC, which actually was broken into two pieces. KDC was broken into two pieces, one called Authentication Server and one called Ticket Granting Server. So the Authentication Server is where all your passwords, etc. will be stored. So that requires a lot of security. Whereas Ticket Granting Server doesn't require that security. Although both of this could be in the same computer because it doesn't take that much power to do either one of the two. However, functionality is separate, and so they just present it always separately. Right? So first thing you do is you authenticate with the Authentication Server. You provide your password or whatever it is to the Authentication Server, and then it gives you a long-term ticket. A ticket that is good for a long time, which is in this case as shown here is a day, it could be an hour, it doesn't matter, long time could be an hour or could be some time. Anyway, with that 1 day pass, with long time ticket, you go to the Ticket Granting Server and you get tickets, many tickets for many different things that you want to do, because once you have authenticated that you are whoever you say you are, then that ticket is good for many things. So for example, you want to print, you could go to Ticket Granting Server and you say, here is my day pass, and I want to use the print server, and then we'll give you a session key that print server will accept. Yeah.
You said earlier that you don't need as much security in the ticket granting server, but it seems like really that's kind of what you need to do in the tickets. So if you could get into the ticket granting server.
Good question. So here the thing, if somebody compromised this, then the problem would be that everybody will get a day pass for a whole day and then maybe for life, right? Whereas here, if somebody compromised this, it turns out that this can be very easily invalidated first of all, and it might do a 1 hour of damage. Okay, so the damage here is very little, as you will see that this one is something that you don't change your password for months and years. If somebody found out your master password, then you have big problem. See what I mean? So the tickets are good only for short time, these tickets, and they expire so fast that if we find out that somebody has taken over our ticket granting server, they won't. Actually, it turns out ticket granting server has really no database whatsoever, and so all they will do is not be able to get new tickets, or some new tickets actually will be issued only if the ticket granting server people who have taken over get the passwords, get the ticket granting server's password, which they could. If they tagged it, they could get the TG's password. If they get it, then they can issue it, but then we can invalidate that in a few minutes. All right. So let me say it again that yes, everything in this chain could be attacked. Say for example, the client could be attacked, right? But that would limit the damage in a space, and then basically we can change the client's password and then invalidate and so on and so forth. Right? Good question. Thank you. All right. So the key things to notice are few things. First of all, that there are two servers. Actually, three in this mixture. One is the servers that you need, and then the two added to that, which is the authentication and the ticket granting. Second thing is that there are two kinds of tickets, the long-term ticket and the short-term ticket, and this is all very similar to what we do, the master password and the session password, master key and the session key, right? Some things are very short-term and you do it many times, and something you do very little, very rarely, so that your security is maximized. All right, so let's go into detail of what these messages contain. I think I have finished all of these. Authentication server is a physically secure node which contains the complete authentication database. So this is something that you don't want anybody to get into. This is logged under key and so on and so forth. Then the principals are authentication server, which is denoted by the letter A, ticket granting server G, client computer C, and user U. Now these two are separate. So my computer is separate than me. Somebody can take over my computer, or somebody can take over me. And so the thing is, U is the user and C is the computer and V is the server that I want to reach. That was the print server. And so each of them have, actually I will come back to this line, but each of them have a key. For example, KCG is the key which is shared by the computer, and the G is the ticket granting server. KCV is the key which is used between the computer and the server that you want to reach. KAG is the key between authentication server and the ticket granting server. And KU is the user's password, and KGV is the G is ticket granting server and V is that server. All right. So some of these keys are generated on the spot, some of them are permanent and so on and so forth, but this is the notation that if there are two letters, they indicate who shares those two, who shares that secret. All right, now ticket granting server we already said is TGS. Tickets. Now ticket is something that is encrypted information that you cannot reproduce. When you get a ticket, you cannot make a copy very easily. If you can make a copy very easily, but that would be very easily, basically you cannot be used again. So ticket is something which is encrypted. It's like a black box to you, and you just have to. So it is encrypted using this, using one of these keys. Ticket granting ticket. Now that is the day pass. Right? That is the thing that you get from the authentication server that allows the user to, the computer to get the ticket from TGS. Sometimes we might use user and computer. Actually, all the time we will use user and computer simultaneous as same way. But basically, there is slight detail here where the user credentials are somehow married with the computer credentials, so we know which server which computer he is talking from, and then authenticated that way. So user is authenticated, but the computer is also authenticated somehow. All right. So these are the main concepts. A few more. Authenticator. So authenticator is actually a field, or just like a ticket. It's a piece of a message where name and the time is encrypted with the session key, and it is sent from the client to the server with the ticket, and from server to the client. So it says, well, look, here is my ticket and here is my driver's license. Right? So the driver's license is the authenticator. Okay? So basically, so that nobody can replay it. It's not like a driver's license is not a very good example, because I can create an authenticator myself. I don't have to go to any place to get that authenticator. It's just my name and my time encrypted with a key that I know. Okay, so that is some kind of secret that is sent. And credentials are basically combination of the two. The session key I know, and I have a ticket. That means I can use the service. And user enters the name and a password, and the client converts the password to a key KU. And then the TGT and the session key are good for a limited time, 21 hours. So when you get a ticket granting server, and I say it's a day pass, it's almost a day, 21 hours. And why 21 hours, not 24 hours? It's basically the way time is coded in so many units and those so many bits. So the maximum you can code is 21 hours. All right. So this is the fundamental. You get a long-term ticket, you get a short-term ticket, and then you can talk to anybody, right? All right. And I would not be surprised. I don't really know. I would not be surprised if we are using this Kerberos system in WashU right now, when you do all this Wushtel key, but I'm not sure. I don't know how Wushtel key works. So, So what is assumed is that the network is open, and so basically everything is encrypted except the first message, and that message is coming up here. Everything is encrypted, and every client and server have a pre-shared secret with AS. So AS is the authentication server, and so every user has to have a password or some secret with the authentication server. It's like your Wustel key password, right? And every service has the same way with the server. So if every print server and any other service that needs to serve the users, they will also have a secret with the KDC, right? Authentication server. And authentication server and TGS are logically separate but share a secret key. So there is a KAG, which is the key between the AS and the TGS. Both AS and TGS are stateless, and that's another strong thing, is that they do not keep any state. So they have given you a ticket, but they forget. They don't have to remember that I've given them a ticket, given you a ticket. So they get your authentication, they give you a ticket, and they can go to sleep. All the state is in the ticket. So anything that needs to be remembered is in the ticket. Day pass is just a longer term ticket. Now, longer term secrets are used less frequently, and short term secrets are created and destroyed after limited use. So that's why we have short term tickets and long term tickets. So that the long terms, you send your user password only, actually you don't send the password, but whatever you do with the password, you do it only once, right? And then everything else is generated and used and destroyed. And of course, there is on all these slides I have put references other than the book, which in most cases is Wikipedia nowadays becoming really good, and sometimes it provides better information than the book. If nothing else, it provides additional information than the book. So let's look at the message. So the first message goes in the clear, everything else is encrypted. E means encrypted, right? So this one goes in the clear and it goes to the AS. So it says, here is your ID, here is my ID, and here is the ID of the ticket granting server that I want to contact. And I'm sorry, this should not be IDA. It should be IDC. So here is my ID, here is the ticket granting server I want the ticket for, and here is the time stamp. Here is the time of the day. It goes to the AS. Now, AS and the client already have a password, already have a secret key, which is established beforehand, right? So AS responds in an encrypted manner and says, well, here are the two things. First of all, here is the key that you can use to talk to the ticket granting server for the next 21 hours, KCG. Okay, it is given to this client. This is a new key. IDG, here is the ID of the ticket granting server. Here is the time stamp 2, here is the lifetime of the ticket, and here is a ticket that you can show to the ticket granting server. And that ticket actually is, so now you see double encryption here. This ticket itself is encrypted. It is encrypted with KG, a secret that G shared with A. Okay? And KCG, this is the same ticket and same new secret that has been generated for the day. IDC, ID of the client. ADC is the network address of the computer. IDG is the ID of this one, TGS, and TS2 is the time, when the ticket was issued and the lifetime of the ticket. All right. So there are two things. One message is meant for the client, so that, and the whole purpose is so the client know what is the key to use with the ticket granting server. Second thing is a piece of information which is encrypted and the client cannot read it. Client cannot decrypt it. It will use it as a ticket. It will show it to the TGS and TGS can read it. Is thus clear that there are two pieces of information. Actually, I mean, this ticket is somehow encrypted, so there is only one thing, but if once the client opens this, it finds two pieces of information. One is the key and the second is the ticket. Okay? If it's not clear, ask me right now, okay? All right. So now the client takes that ticket and sends it to the TGS and says, I want to use this server V. Please give me a ticket for that server V. So let's see what it does. It sends the ID V. ID V is the ID of this server. Ticket that I have gotten, the long-term ticket, authenticator C, and authenticator is shown in the next line, but anyway, so these are the three pieces of information which are sent here. The ticket itself is as before, the same thing, and basically encrypted thing, and the authenticator is my ID, my address, current timestamp, and whole thing is encrypted with the new key that I have gotten from the just now, for this pass, for this day. So this KCG is the day ticket, day secret, and basically here's my name and all that. So the reason this is sent is so that it can match these two and say, yeah, the ticket is for the same person who knows this secret KCG. Alright, so nobody else can use that ticket. Alright, so then it sends a short-term ticket, basically again consisting of two parts. One is a ticket which can be used, a short-term ticket which can be used with the server, and a new key that can be used with the server. So read carefully. This ticket is encrypted with what key? Sorry, not this script. This message is encrypted with what key? Anybody knows the key for this first line, line number 4? KCG, which is the day secret that the client and the server TGS share, just for the day today. And so both of them know that. So this one encrypts that. And then once the only person who can decrypt is client. Once the client decrypts it, it will find these pieces of information. It will find KCV. That is the key that can be used with the server V for the short time. And the ID of the server V, the time of this key, and the ticket that you can be given to server V. Now that ticket is encrypted. It is encrypted with KV and KV it encrypted with KV, so only server V knows this is server V's key. Actually, that is kind of the reason I stopped right there is that I said that the TGS does not know the secret, but it looks like that this V, if TGS knows, then it does have this secret. The TGS knows the secret of all these servers. So anyway, it knows KV and it encrypts that, and it tells with this ticket it can tell the server that the session key is KCV and that client is IDC, his authenticator is ADC, you are IDV, this is the time and this is the lifetime. So all of this is basically giving the key to the server. Now the key, the ticket is simply returned to the server by the client, and by using this ticket, the client knows what is the key to use. And then the second part is authenticator, which as before is basically ensuring that nobody else can take that ticket. So this authenticator ensures that this ticket is being sent by somebody who knows KCV, who knows the key, and then for that identifies, so KCV. So anyway, so now the server can identify that thing, and then it sends this TS5 back. Why TS5 is sent back? Because it sends TS5 plus 1 or any function that could have been agreed. In this case it was agreed that TS5 plus 1 will be sent. Basically it says that I know CV, so I am V, and so I can decrypt this ticket, right? And I know KCV, and so here is your proof. Alright, if it goes to some other server, the other server will not be able to decrypt this ticket and will not be able to return this part. Alright, so there is a mutual authentication. The client authenticated with the server and the server authenticated with the client. Now it might be good just to go over, there is a lot of symbols here, that's why I first prepared this other slide, which is basically, that has no symbols, has just the meanings. And then we have this slide, which is the same messages but in symbols, so that you understand the meaning. Yeah.
So going back to the ticket G up at the top, it includes the address of the computer that's
Requesting it.
Oh, yeah. So does that imply that that computer can never get a new network address, so wireless?
Oh, if it changes something, then it will go, it will have to re-authenticate.
Okay.
Yeah, that's correct. I mean, first of all, I mean, that brings up a new point, and that is that what about mobility? Right? You said wireless is that if you move, then you have to re-authenticate, you go from here to library. This was designed in 90s. This wireless didn't exist then. First of all, people didn't move that fast. Now, yes, that's the concern, that you would not authenticate based upon an address. You would probably authenticate based upon an ID, which is your MAC address maybe, right? So you can authenticate not based upon IP address. So you could authenticate based upon your MAC address, and then you go to some other place and you put your MAC address. So this will have to redesign for mobile systems. Okay. Also notice that when the user goes to some other computer, they really have to re-authenticate, because that other computer does not know any of the secrets, user secrets. Okay, any other question? So basically, let's see. As I said before in the introduction to Kerberos, this is very commonly used today in many different contexts, and so this has proven successful. I remember hearing a presentation from the inventor of Kerberos. He was our colleague actually from Digital. And in those days, we never thought it would be so popular, so famous, Steve. But now it's all there. Anyway, so if you want to go to another realm, suppose you want to use the services which are not in the same realm. What is a realm? A realm is AS and TGS. So each realm has its own authentication server. So you are authenticated with Wustel and you want to go to St. Louis University and want to use a printer there. That's a different realm. They don't have your password. They don't have your username. So how do you do that? Well, basically, our authentication server will set up a password with their authentication server. So these two will know each other. Right? And once they do, then we all are authenticated. How? You say, well, I want a ticket for the local TGS. And you go to local TGS and say, I want a ticket for the remote TGS. And since they share a secret, just like a server TV, we had we had a server, we had a secret with the server, we have a secret with the TGS, so it can issue a ticket for the remote server, remote TGS. Then it can go and say, I want a ticket for this printer, and you can get the ticket as usual. All right. So, and notice that none of this uses any of the certificate stuff. So no public key, no certificates. It's all based upon secrets. This is early 1990s technology. So 20 years ago. Okay, so CBC is what? Cipher block chaining. If you remember, in cipher block chaining, we used to take the cipher block from here and chain it like that. That has some problems. And one of the problems was that some of the times the error could go undetected, and there were some attacks that people designed. So by the time this was designed, Kerberos was designed, they changed the cipher block chaining to PCB, plain text and cipher block chaining. So you chain the cipher block and you change the plain text, both. All right, PCBC. Now with that, what happens is, if somebody changes one bit anywhere in any block, then everything will change. Okay, you did this homework. I think if you remember, you did one of the homeworks where we asked you how many blocks will be changed with some errors, and there was 2 blocks and things like that, right? So with PCBC, all the blocks will be changed. So it just provides better integrity. Now, still with Kerberos version 4, while it was good for MIT, as we started adopting it, there were lots of problems, and the Kerberos version 5 had to be developed. So what are the problems with version 4? First of all, everything was non-standard. Names, instances, realms, everything was limited to 40 characters, and non-standard in the sense that the coding that was used was just somebody's, whatever they thought is right, they did it. For example, your name always ended with a 0, null character, and so that itself is a problem. That itself is a problem, because people have found out ways to attack by putting a null in the name, and things like that. And they were limited to 40 characters, which is not sufficient for many things. So second thing is DES encryption. So they only use DES, and we know the DES is no longer good. So we could not use AES because it was just built into the protocol. Only IPv4. It was built into the protocol. All the addresses were 32-bit long. You could not use any other protocol such as ISO CLNP. Any guesses what that might mean? So ISO, we already know, is International Standard Organization. CLNP is Connectionless Network Protocol. So ISO also developed all these protocols. Then there were layer 3, layer 4, layer 5. Sorry, layer 3, layer 4, and layer 5 is application layer. And many of them were implemented. Even though we don't use them very often, but they exist. So there is a ISO network layer protocol, connectionless network protocol, which would be a replacement for IP. They never replace IP, but it exists. So now people want to make sure that that is supported. Names should be encoded by ASN1 because ASN1 is designed for encoding names. And that is what is used in all other places for encoding names, such as in certificates. So that way you can use ASN1. If you use ASN1, then you can use any byte ordering. Right now the byte ordering is indicated by, basically in the message. Okay. Then maximum lifetime is 21 hours because 8-bit lifetime in units of 5 minutes. So 5 minutes times 256 is that 21 hours. Right? The time is 8 bits, 1 byte, and each bit indicates 5 minutes. 21 hours. No delegation. A server cannot allow another server on the behalf of the client. So you could not go to a print server which could give it to another print server. So it's just direct. Okay. Inter-realm authentication limited to pairs. So everybody has to have a secret with the TGS, particularly if they have another realm, their TGS have to have a secret with our TGS, and it has to be direct. So we could not trust them and they could not trust somebody else. So A trusts B and B trusts C does not imply A trusts C, which is a good principle that I cannot trust somebody that you trust, but then it becomes less scalable. Then it becomes difficult to cover the whole world there, cover much longer area, because then you have to know n squared secrets. So in some cases it might be okay for you to use that, and so that is where that needs to be generalized. Double encryption of the ticket. So remember, the tickets are encrypted inside the key. We noticed that one here. This ticket is inside this key, KC, and the ticket itself is encrypted stuff. So why do we need to do double encryption? That is just extra work that we don't need to do. PCB does not detect interchange of cipher blocks. Interesting. So basically, while it propagates the errors to all the blocks, but it has some of its own weaknesses that was not discovered when it was designed. And no subsession key for long sessions. So we got one KCV, which is the secret between the client and the server. And if that session was very long, suppose you wanted to use, it was not a print server, let's say it was a database server, and you wanted to use it for a day, then you don't want to use that KCV for a day. You really want to break it down into hours or minutes or something like that. So that was not allowed. And brute force password attack. And there was some way to attack the password. And so anyway, so these 11 things, I have double numbering here, but basically I should have deleted these other numbers. But 11 issues, they were fixed in version 5. So now the names, instance, and realms have ASN1 names, They can be of any length. Any encryption scheme can be used. So now encryption scheme is coded. So you'd say that I'm using AES. Hey Brandon, you can sleep in the next class. 473. I know you guys are working hard. So any type of addresses can be used. The address type is specified. Byte ordering is ASN1. The explicit start and the end time, so there is no business of 1 byte with 5 minutes. So you can have any lifetimes. Delegation is possible by requesting proxyable tickets. So you could say, I want this ticket that can be assigned from one server to the next. It's a weaker ticket, but you get that ticket, proxyable ticket, so that proxy can use it for you. Inter-realm authentication hierarchy, and that A trust B, B trust C is allowed. So A trust C. No double encryption of the ticket. So ticket is kept separate outside of the encryption. Explicit integrity mechanism detects block interchange, so that PCBC was fixed. Sub-session keys for long sessions, so you could get keys for shorter time. And password attack is made difficult by a pre-authentication mechanism. So all of these problems are fixed. Yeah.
So are the secrets, do the authentication servers still share have shared secrets between them?
Okay. Let me see your question. So authentication server, you are saying different realms? Yeah, right. The authentication server in real different realms have to have a secret with somebody. And so let's say if Vashu already has somehow secret with the rest of the world, then if a new realm comes in, all they have to do is just have a secret with Vashu. So then A trust B and B trust C, you can authenticate that way. You don't have to have A and C directly share the secret.
But so if you were to compromise one of the servers, would you then have the...
You have to remove it, yeah. See, the thing is, it's like any other servers here. If one of the servers is compromised, their keys have to be removed. And in this case, if that server happens to be TGS for another realm, then that realm has to be removed until that is fixed. I mean, remove means they will get a new secret done, and then the life will start, but the previous tickets may not be useful. There is some disruption. Good. Any other question? All right. Kerberos version 5. So now let's look at the messages. We just finished the 11 things, but let's see. So the first message, which is not encrypted, has these things. It has options, IDC, realm C, IDG, times, and nonce 1. Alright, so the options might include that I want proxy and I want long term and I whatever else you want. So there are many options that we'll talk about, but those are the things which we tell the AS that this is what I need my ticket to have. This is my ID, this is my realm, and this is the ticket granting server that I want, and so on. Now AS will send you, repeat whatever you have said, and then send you a ticket, send you a new key for the ticket granting server, right? And obviously it is encrypted, whole thing is encrypted, so nobody else can read it, even though they can read the clear part here. This part is in clear. Well, let me correct myself. The ticket is in clear, but ticket itself is encrypted, so it's not really in clear. I mean, ticket itself is encrypted. These two are in clear. Ticket itself has is basically encrypted with KAG. It says what flags the user requested, and the rest of the stuff should be obvious. You know, here's the key to use and the realm and so on and so forth. Then the client takes that thing and sends it to the TGS. The important thing is, and it creates a new nonce and everything else, but the important thing is everything is clear here except for the ticket and authenticator. These two are encrypted. And they go to the TGS. The TGS sends back the ticket for the server, and everything else as is before. Basically, this is the encrypted stuff with a nonce. Yeah. Okay. All right. All the keys are labeled by 2 letters or 1 letter. If it is labeled with 1 letter, then that is the secret you share with the AS. And if it is labeled with 2 letters, then it indicates the 2 principals that share that secret. So A is for authentication server and G is for TGS. So KAG is the secret that is shared permanently, actually in this case permanently. Not everything is permanent. For example, KCG is not permanent. KCG is generated every day. But KAG is permanent in some sense. So KAG is the key that is between A and G. KCG is the secret between C and G. Now this is we just got it as a part of our request, and so this is basically for today's use. All right, so let's look at other keys. When I say KG, actually that was kind of KAG was strange because KG is same thing as KAG. KG is the G's secret that it shares with the authentication server, right? Which is KG, and so this ticket sorry, this line is out of place. This line should go up here. So this is basically a detail of ticket G, which is in this line here. And so in this line, basically server sends only the ticket for V, and the ticket V is explained here. Okay, let me see if I can fix that quickly. I don't think I can fix it very quickly, but this line, Control X, should go here. And this line Control X should go here. All right, now this line should come Control Z. I'm lost in this picture. I can't even see anything. How do we fix it? Ticket authenticator. I put authenticator somewhere. It's overlapping. Okay, now it's fixed. All right, so this is in this one we have two things, ticket G and authenticator C. This is the ticket and this is the authenticator. In this message which goes from TGS, we have ticket V, and that this is the details of ticket V. Now ticket V is obviously encoded with KV, so the client cannot read it, but it sends it straight to so it sends it straight. So this one actually come on, it doesn't help. Okay, better. All right, so this line was wrong. This is authenticator C, not V. So this client sends the ticket and the authenticator ensures that basically, and this one can verify that basically I know the key. And then once it knows the key, it sends back the ticket and then something back which verifies that I know the key. Yeah.
So can we download the revised version online?
Okay. So the question is, can we get Kerberos version 5? I think so. Well, here's the thing though, I will have to go and check it myself. I have not checked it. Kerberos version 4 is free download from MIT. That I know. Kerberos version 5, I would be really surprised if you cannot download it, because nowadays everything that is security is open source. So somebody would have made an open source version of Kerberos 5. Almost everything. Okay? So just look. I mean, just you have to say Kerberos V5 open source. You will find it. Any other question? Yeah.
So could someone put up a Kerberos version that they made open source that has a backdoor hit somewhere?
Okay, so if you work for a company, you can do anything. If you work for Bashu, you could probably, play with Bashu's security system as much as you wanted to. Although if somebody else figured it out, then they will, ban you for life. So the thing is, there are two things. I mean, when you compile these sources, you could add instructions, and then really, you could put yours. But this being security, I'm sure that the organizations that do this, they have both the white team and the red team. white team are the guys who are working, and the red team are the guys who are testing them out. And so the red team would catch you, someplace. But, not all companies are as smart. And so they might just have one person taking care of the whole thing, and in that case, that person has complete control. Okay? All right, so flags. So these are new things. So we talked about options and flags. In the options, the client tells the server that this is the option flags I want, and those are the flags which are set in the ticket, right? So initial. So this is a ticket issued by AS. All right, that flag will be set, and that will generally, in the previous description, it will be only set on that TGT ticket, ticket granting ticket. That is issued by AS. Pre-authent. The client was pre-authenticated by AS before a ticket was issued. So this will generally be issued set that the client has been authenticated. But it is quite possible that the client has not been authenticated. All right, then there will be some additional authentication required. Hardware authentication. So how authentication was done? It was done using hardware like a smart card or something that the user purchased. So you know what is the quality of authentication. Renewable. The TGS can issue a new ticket that expires at a later date and therefore allows long lifetime. Previously it was limited to 21 hours, and even if you have some different units, so you could have a longer lifetime ticket. So these are renewable tickets. May post date. So this is another feature that you can issue a ticket which is in the future. And if it is a ticket in the future, then it is post dated, and so it might be, let's say, in 2012. So then it will be also be, generally there is another flag somewhere, it is coming up here, yeah. So this ticket will be, this is what will the AS will say, that you can post date it, and if it is post dated, then TGS will set this flag, right? And a ticket which is post dated is generally invalid. That flag is set. So before it can really be used in 2012, you have to go back and validate it. So there is the state. See, now previously in version 4 there was no state. Now here is some state. So anyway, so this ticket is proxyable. This can be proxied with a different network address. So the network address is not fixed. And proxy, the ticket is, so proxyable is the one that is set by the authentication server. So authentication server tells TGS that, okay, you can issue a ticket which is proxyable, and then when it issues a ticket which is proxyable, then the TGS sets this bit which is proxy. Forwardable, that this can be forwarded, and then if it is forwarded, then it is forwarded ticket flag. So there are two flags: proxyable, proxy, forwardable, and may post date and post date. So those are flags. Okay. So the forwarded ticket is the one that can be forwarded by one server to the next. So A can get a ticket to Y.C via B, and so it can forward, can say to B that here's my ticket, and then can be forwarded to C. So rather than directly going, then the ticket goes like that. All the transient realms in the path are put into the ticket. That way you can check it out whether you want to accept that ticket or not. For example, if you get a ticket, let's say, just to name a country, suppose you get a ticket, and you get a ticket which came through some Russian validation. Now you are Defense Department in the United States, you may not want to trust it, right? So the whole path of where the ticket has been authenticated is put before you trust the chain. So anyway, so let's see if there are any more flags. No, that's it. So these are all the new flags, including an invalid one. So somebody may ask you why you have to issue an invalid ticket. Well, the reason is the ticket is invalid today, but it can be validated later on, post-dated ticket, yeah.
Why would you want to post-date a ticket? Like, is there an example?
Yeah. So sometimes, I mean, now this is, I'm just guessing here, is that you want to have things that either continue for a long time, and it's not worth starting if they cannot continue for a long time. You may want to run a very long batch job, which is good for tomorrow. I will run till tomorrow. So I really don't want to start it unless I get a ticket for 2 days. So you get a ticket for today, and then you get a ticket for tomorrow. And the tomorrow's ticket you have to come back again. But the good thing is that you already got the ticket. You don't have to go to AS server again. So that's all it does, is it saves you that going back to AS server. You can get it validated again from TGS. I don't know whether that is a big deal, but that's, yeah. You don't have to go to AS again. You can get all the tickets for the future for that job, and then you can keep going to TGS to validate them. All right. So this is all actually. I think we finished Kerberos. Any question about Kerberos before we go into a totally different topic, which is public key? So Kerberos does not use public keys. Kerberos uses only secret keys, right? And we have two versions, version 4 and version 5. And version 5 is the standard version now, basically standardized, generalized, and so on and so forth. And we saw these generalizations, and we saw how it makes use of KDCs and the tickets. Right? Any questions about Kerberos before we move on to the different topic of user authentication? Well, nowadays we can use certificates for authentication. So if you wanted to use certificate, then the certificates could be kept at KDC. Right? And so if you want to talk to A wants to talk to B, then it could go to B and say, please give me the certificate for B, and you will get the public key for B. Now the reason you want to get from KDC is that now you are basically, you can trust that information. It is encrypted with the private PR. PR is the private key of the authenticator, KDC. Everybody knows the public key of the authenticator, right? So with that you can get the public key of B, PUB. Then you can send the message to B. By the way, you also get the address and ID of B. So you can send the message to B, ID you already sent anyway. Send the message to B and you can say, here's my nonce, and the message is encrypted with your public key. So if it reaches the right place, it wants to make sure that it knows the public key of A. So it goes to KDC and says, can you give me the public key of A? A sent me this nonce and A, and what is his public key? So the answer comes back, here is the ID and here is the public key of A. And here is the public key of A, and here is your request. Here is your request. PUB, PR authorized, NA, this is the nonce you sent me. Here is the session key, and here is the ID of A and B. So there are two things here. Here is the public key of A and here is the session key. Session key is specified here, right, along with the nonce. So then B responds back with, here is your nonce, here is my nonce, and here is the session key. Now prove me that you understand all this. So it says, yep, I understand, here is your nonce. Alright, why are we using nonces? So that we can prove that this other side has the key. If the other side cannot tell us the nonce, means they don't have the key. So the nonces, A sends a nonce to B, which is actually in the clear. No, it's not in the clear. It is actually encrypted, so it wants to make sure that somebody who has the private key of B will only know NA. Right? And this one is encrypted with two keys. And so somebody who has the private key of A and public key of authentication server will know this, and B. Right? So here is your nonce back. And so KS is the session key that they can use from now on. Yeah.
Sorry, the second step here, like here's the public key of B. If that's encrypted with the private key of the KDC,
Yeah.
how do you?
So everybody knows the public key of KDC. Everybody knows the public key of KDC. So this, remember, this is asymmetric encryption. So anything that is encrypted with the private key is decrypted with the public key. Anything that is decrypted with the encrypted with the public key is decrypted with the private key. So everybody can decrypt this. Yeah, that's a good question. Maybe this is the question. Is that actually it doesn't have to be A, even C would know PR authentication, public key of authenticator, and will get IDB and PUB. Alright, but that's no big deal. Right? Anybody can decrypt that message and find out what is the public key of B. It's no use, basically. Right? So, yeah. And let's see here also same thing. If anybody can decrypt this message, but it's no use. But nobody can decrypt this message. All right. Okay. Now, what if you have to do one-way authentication, which is generally done in the mail? When I want to send you a mail, I want to send you a mail where you can verify that it came from me, the signed email. All of you got from, for example, from Mart. That was one way because he didn't know your certificate, he just sent you an email, which you could verify that it came from him because he signed it. And so this is how that works. Because the message is long, we don't use the public key for message encryption. We encrypt the message with a secret key, right? Any random secret key I can select and I can just use that to encrypt. But I send that key to you along with the message. That key is encrypted using public and private keys. Okay? So for encryption, better to use secret key and then the secret key using public key. So A to B, here is my public, here is the secret key KS. Secret key KS, which is encrypted with public key of yours. Okay, so here I think this you could not do if you didn't know the public key of B. So if I didn't have your certificate, I cannot send you an encrypted email. Alright, so what I can do though is I can send you a signature. A can send to B a message which is in clear, and I can send you my certificate. I can along with this certificate I can send you a hash of this message, hash of that message using my public key, which is signed with my private key. Anybody can check it out with my public key. If they have my certificate, they can check it out. So that's what we did, was basically if somebody changes the message, then when the receiver can say, well, the message has been changed, sorry, this signature is invalid. I don't know, George, were you able to resolve that ever, or your signature is always invalid?
I was able to get an email from the TA and send a response back.
But you had to manipulate something. What was that you manipulated?
I don't know that we exchanged copies.
Yeah, okay. All right, so some companies I think do play with these messages, and you cannot send signed messages because the message will be changed. They might add things like disclaimer that this message is only for public business use, blah blah blah, and we don't take any responsibility, this and that. If they add anything to the message, your signature is no good.
Yeah, I remember they were using, it was a Boeing thing, and
Yeah.
Boeing is in the chain of trust.
Yeah, it's a Boeing, but not in our chain of trust.
Right.
Yeah.
Yeah, that's what I was going to say.
Yeah.
That's what I thought.
Okay, so I think the problem in this case was different. The problem was that his certificate was signed by a CA that we didn't know. That was not in our systems. So we could not verify the certificate. Anyway, so everybody understands that how I can send you a signed message only if I don't know your public key. That means if I don't get your certificate. But when I send you a signed message, what I'm doing is I'm sending you three things. I'm sending you the message in clear. I'm sending you a hash which is using my private key. So it is guaranteed that I sent it. Anybody can verify that with my public key. And I will send you a certificate along with it. Right? Now that certificate you can import in your Outlook. So you have my public key built in now, right? So that is why we needed to go to the second step, which is encryption. I need the public key. That I can do only once I get a certificate from you. However, note someone else can replace the signature and encrypt the message and signature. Can replace the signature and encrypt the message and signature. A to B, here is a message with public key PRAHM . So recipient must know the A's public key. Yeah, and therefore A certificate is sent with the message. Yeah, so that's correct. Basically, if I don't send you the certificate, then somebody can just manipulate both the signature and the messages with any private key, right? So C could use its private key and say I am A, and here is the signed message. But that cannot be done if you have a certificate which is signed by somebody that we know. So actually that is what we did. We just accepted a certificate that was signed by somebody we don't know. Alright, so that's trivial. We already did this exercise. Now we understand why we need the certificates first and why we need to send a signed message first, and then we can do the encryption. Any question about this procedure? I think I will have to stop right there. Because